Now, we want to move on to simultaneous equations. It's going to form a major component of what we do throughout year 11 and 12. So it's something we need to be very, very good at. So the concept of simultaneous equations is just this. If I gave you the function y was equal to 2x plus 1 and asked you to graph that, it's a pretty straightforward one to graph. So this cuts through 1 on the y-axis, goes up 2 across 1. Okay. So that line there represents the infinite number of possible solutions to this. So there are an infinite number of combination of x, y points where the y coordinate can be generated by the x coordinate being times by 2 and have 1 added to it. Now, if I were to give you another equation, such as y is equal to negative 3x plus 11, and we were to graph that one, that's going to cut through up here in that positive 11, have a downward slope. It's going to be shaped something like that. Now, once again, this function also has an infinite number of solutions that obey the rule the y coordinate is equal to, as it says there. But there is one point, and one point only, that exists on both lines at exactly the same time, simultaneously. That particular point there, its x coordinate and its y coordinate solve this function and that one down there. This is what we're going to be working on, is how to solve these particular equations so that we find the point of intersection. So if you ever hear anyone say the simultaneous solution or solving simultaneous equations, we're finding where two lines intersect, and that's all it comes down to. Now before we start, just got a big picture idea for you. If I gave you, for example, 2x plus 1, that's called an expression. Now, we can't solve that because it's not equal to anything. Only when two things are equal are we able to solve for unknown values. So that's just a statement of some sort of fact. If I now said that the 2x plus 1 was actually equal to a certain value, I could find the one unique solution to that, where x would be equal to 4. But if that's what we call an equation. If I then said the 2x plus 1, instead of being equal to one specific value, like it is here, I made it equal to an infinite number of values, we now have a function. And of course, as infinite solutions are represented by wherever the graph is. Now, so when we come over to this situation here, if we look at y equals 2x plus 1, there are an infinite number of solutions. We can't drill down to any one in particular that's going to be useful. Same with the second, the negative 3x plus 11, infinite number of solutions. So when you have a situation where you have an equation that's got two unknown values, my y value is unknown, my x value is unknown, there's two unknown values, you have a function, infinite number of solutions. We need to reduce this down from having two unknown values down to having only one unknown value. And when we do that, we're able to start working out what the coordinates of that point are. Now, there's three different ways that we're going to be looking at it. One is graphically. You can see here, I've drawn a graph of each, and I just read off my graph what the x-coordinate is and what the y-coordinate. It works. It's a bit difficult because you have to be super accurate for it. You might want to do up a table of values for both functions and see which particular point appears in both tables. That's also a graphical solution. That implies that you're going to have whole number values of x and whole number values of y as your solution, and that won't always be the case. Some other ways that we're going to do it. One is called the elimination method. So one of the unknown values we will eliminate so it's no longer present. And there's one called substitution. I just want to talk about substitution first. Now, before we do substitution, I want to show you something that, see if you can make sense out of this particular logic. If I told you that I had a boy in my class whose name is John, and he was exactly the same height as Peter. Then I had another boy in my class called Mark, and I told you that he was exactly the same height as John. It shouldn't be too difficult a concept that if Peter is the same height as John, Mark is the same height as John, I can therefore say that Peter and Mark must be equal to each other in height. Straightforward enough? Yes. We're going to use that exact same concept over here with these two. If you can wrap your mind around Peter and Mark both being of equal height to an in-between person, so therefore they're equal to each other, exactly the same logic can be applied over here. Can you see, if I can say that Peter and Mark are the same height because of this situation, can I apply exactly the same logic to this? Yes, I can. Well, according to my equations over here, y is just a number. It stands for a value that we don't yet know. Apparently, y is exactly the same size as 2x plus 1. Now, down here, same y, same value. Apparently, it's exactly equal in size to negative 3x plus 11. We have the same situation appearing. 2x plus 1 helps produce the y value. Negative 3x plus 11 produces exactly the same y value. What statement can we make? These two expressions must be equal to each other. Look what I've got. Instead of having an equation now with two unknown values in it, I now have an equation with only one unknown value in it. And by simple year 9 level manipulation, we can rearrange that to work out what the x-coordinate of the point of intersection is going to be. This is called the substitution method. So if I take my minus 3x from the right hand side and bring it to the left hand side, I leave my 11 on the right and bring my minus 1 over to become take away 1. 5 of those unknowns are equal to 10. One of those unknowns must be equal to 2. My x-coordinate must be 2. How do I work out my y-coordinate? Well, I've got two rules up here that tells me how to do the y-coordinate. This one here says that the y-coordinate is equal to 2 multiplied by the x-coordinate with 1 added to it. So the x-coordinate must be 5. Sorry, the y-coordinate must be 5. We'll give our final answer then. So therefore, the simultaneous solution is 0.25. And that's simultaneous equation, the beginning of it. I'm going to rub this out, and on the next video I'm going to show you another one of substitution before we go on to the other methods. I'll see you on the next video.